Alright, sorry for the delay. Are we ready to go? Alright, Jerry Dunifer is a Professor Emeritus at Wayne State University. He was a member of the faculty in the Department of Physics and Astronomy for 35 years before retirement. While active in the department, he served as a professor and associate chair of the department for several years. His research program there involved the study of electrical and magnetic properties of high-purity metals at a temperature of 1 Kelvin. He also played an active role in the astronomy programs at the university, including the Wayne State Planetarium and telescopic observing facilities. Since retirement, one of Jerry's hobbies, which you've all heard about, has been visiting a number of the major and historic astronomy observatories around the world. He has visited dozens of sites and has traveled as far as the geographic South Pole and the geographic North Pole, so it's really hard to go any further. Although I hear he might have his sights set on the moon. And he has been many places in between, including many times on the stage. So I give you Dr. Jerry Dunifer.
Thank you, Jonathan, and good evening, ladies and gentlemen. So the first slide, this is Barnard's star, with a few background stars around it. Another picture of Barnard's star. This turned out to be a very interesting star. It has some interesting characteristics and an interesting history. First of all, it is one of our nearest neighbors in space. So it's indicated in this slide. If we have the sun down at this location, and we go up by 2 light years, 4 light years, 6 light years, the nearest star system is Alpha Centauri, which is a triple star system about 4.3 light years from Earth. And then second furthest is Barnard's star, at just about 6 light years. Also shown here is the outer regions of the Oort cloud. The Oort cloud is a cloud of comet nuclei, which extend about 1 light year out into space, and this is the sort of outer regions of our solar system. Now, the distances that were indicated are only true for the current time because all the stars are moving relative to each other, and these distances change. And that's indicated on this slide. So looking at distance from the sun in light years versus time horizontally, 0 time corresponds to the present day, and then going to the right, we increase in time in thousands of years, and going to the left, we go back in time. So right now, at the present time, Alpha Centauri is about 4.3 light years away, and this curve, which is Barnard's star, is about 6 light years away. But as time goes on, we see that both stars are moving in our direction, and in about 10,000 years, both stars, Barnard's star and Alpha Centauri, are going to be at about the same distance and about 4 light, or less than 4 light years from the sun. Then after that, Barnard's star is going to be retreating, and Alpha Centauri will continue moving closer for a while. So here are some of the properties of Barnard's star. It's a cool red dwarf star, has a spectral class of M4. It has a radius which is about 1/5 that of the sun, a mass which is about 1/7 that of the sun, surface temperature of about 2,900 degrees Celsius, and the sun is about 5,500 degrees Celsius for comparison. The star has a visual luminosity referring to the number of watts that is radiating into space in the visible region, which is only 0.04% of that of the sun. Even though it's very close, it's a very faint star. Its apparent magnitude 9.5, which is too faint to see with the naked eye. You need either binoculars or telescopes to see. Appears to be about 10 billion years in age, whereas our sun is less than half of that. The metallosity, which is the elements which are heavier than helium, are quite a bit less than that of the Sun because of its old age. Rotates on its axis with a period of 130 days. Then the constellation of Ophiuchus, and a distance that's a little under 6 light years. So if we make a comparison to our planet Jupiter, we see there's not that much difference in size. Barnard's star is about twice the diameter of Jupiter, although it's about 150 times the mass. So it has a much higher density overall, with an average density about 20 times that of the planet Jupiter. So if you want to find it in the sky, the summer is a good time to look. So looking up in the sky, as described earlier, we have the summer triangle, Deneb, Altair, and Vega. And a little bit off to the right, we have the constellation of Hercules, M13, the famous globular star cluster. And then down further to the south, it is Ophiuchus, with the 3 brightest stars, Alpha, Beta, Gamma. And here is Barnard's star, right down here. So, who was Barnard? Edward Emerson Barnard, commonly known as E. E. Barnard. He was born in December 1857, died in February of 1923 at the age of 65. He was an American astronomer. He was considered by many as the greatest observational astronomer of his time. His father died before he was born, and he grew up in poverty. He had essentially 0 formal education. And at age 9, he started working in a photography shop to earn extra money to help support the family. As he grew older, he got very interested in astronomy, and he bought his first telescope at the age of 18, a 5-inch refractor, which is a fairly serious telescope. Here he is a little bit earlier than that previous picture, standing with a 36-inch refractor at the Lake Observatory in California. So some of his accomplishments, he joined the staff at the Lake Observatory at the age of 30. He discovered the moon Amalthea, one of the moons of Jupiter. This was the 5th discovery of a moon since the 4 earlier discoveries by Galileo back in 1609. So a length of time of 283 years went by before the 5th moon was discovered by Barnard. Amalthea is a fairly small moon. It's about 150 miles by 90 miles or so, sort of potato shaped. Very hard to see, but Barnard was known for having exquisite vision. He was a pioneer in astrophotography. He determined that the dark areas of the Milky Way was not just the absence of stars, but actually the presence of dust clouds covering up stars which were behind them. He compiled a catalog of dark nebulae, and he discovered 15 comets between 1881 and 1892. In 1895, he joined the University of Chicago as a professor of astronomy. He observed the shadow of a ring spoke on Saturn's moon Iapetus, and this he didn't know what it was at the time, and this was not actually confirmed until Voyager 1 made a close encounter to the planet in November of 1980. He used a 40-inch refractor at the Yerkes Observatory. He observed emission lines in nova, which he observed in 1892, determining that the event was actually an explosive event. So what is the connection to Barnard's star? Barnard measured the proper motion, which is the angular velocity of the star across the sky, and determined it to be 10.39 arc seconds per year. Proper motion is usually described by the Greek letter mu, and this turns out to be the highest proper motion of any star in the sky. If you live to be 87 years old, then during your lifetime, Barnard's star will move 1/4 of a degree across the sky, which is 1/2 the diameter of the full moon. So for making that measurement, he was honored by having the star named after him. If this is the sun, and this is a distant object like Barnard's star, and the object is moving through space relative to the sun at a velocity we call the space velocity. For Barnard's star, this is about 88 miles per second, which is very high for a star. And the fact that it's very close gives it a large proper motion. So if the space velocity is divided into two components, one the radial velocity parallel to the line of sight, and the other the transverse velocity perpendicular to the line of sight, then the radial velocity moves the star closer or further away from the sun, and the transverse velocity moves it across the sky. And in 1 year's time, the angle that it traces out is what is called the proper motion, mu. So here's a picture which was taken over a 16-year period, showing how Barnard's star has moved in 16 years. So these are 6 individual exposures. And here we see a 20-year period and how the star has moved during that 20 years. And notice how it is moving relative to background stars. Background stars are hardly moving in comparison to Barnard's star. This is a set of pictures, exposures taken by an amateur astronomer, Rick Johnson, who lives in Lincoln, Nebraska. For these exposures, he took 1 picture per year, always in the month of July. And so you see them equally spaced in time. That is Barnard's star. So another name which is associated with Barnard's star is Peter Van de Kamp. He was born in December 1901 and in the Netherlands, and he died in May 1995 in the Netherlands. But between those dates, he was a professor of astronomy at Swarthmore College in Pennsylvania. My wife Carolyn knew him quite well because Carolyn did her undergraduate studies at Swarthmore College, and as a sophomore, I think, she took a class in Russian, and sitting beside her was Peter Van de Kamp, who at the age of 70 decided he would like to learn Russian as well. So a little bit about Peter Van de Kamp, professor of astronomy and director of the Sproul Observatory at Swarthmore. He used a telescope there, which was a 24-inch refractor. His specialty was astrometry, the precise measurement of a star's position and its motion across the sky. For example, he measured the proper motion of some 18,000 stars over 8 years. However, during the 1960s, he reported that there were wobbles in the motion of Barnard's star, which was indicative of a planet in orbit around that star. He first claimed 1 planet, and then later on he claimed that there were 2 planets. When he was claiming 1 planet, he said that it had an apparent mass of about 1.6 times that of Jupiter, therefore a gaseous giant, and about 4.4 astronomical units. Astronomical unit is our distance from the sun. Later on, with 2 stars, he said they had masses of about 1.1 and 0.8 Jupiter masses. But that was a long time ago, and things have changed during that time. This is a telescope which he used, 24-inch refractor, a Sproul refractor. This is the way the wobbles could come about. If you have a planet in orbit around the star, the gravity of the planet pulling on the star causes it to move as well. And in fact, they both revolve around a point called the center of mass. So as the center of mass moves through space at a constant velocity, the star itself can wobble back and forth around the straight line motion of the center of mass. And here is Peter Van de Kamp's data. He took thousands and thousands of photographs, and he's looking at deviations from a straight line path. And looking at the photographic plate, he's making measurements of 1 micron, plus 1 micron, minus a micron. So a micron is 1/25th of a thousandth of an inch. So it's a very, very tiny measurement on the photographic plate. And you can see what 1/100th of a second of arc looks like. So we looked at deviation from the straight line motion, both in right ascension and in declination. And this is the data which he got. Now, because of turbulence in the atmosphere, you take a photograph, the star doesn't show up as a point, but rather as a rather fuzzy blob with a typical diameter of about 1 second of arc. So he is measuring the center of this blob to a tiny fraction of that blob. So in the last 50 years, what we've discovered is that the claims of Peter Van de Kamp about planets going around Barnard's star, in fact, was spurious data. They're not really there. The claim was an artifact which is caused by removing, cleaning, and making adjustments of the primary mirror several times. However, much more recently, in November 14 issue of Nature magazine of last year, was an announcement of a new planet going around Barnard's star. And this was very, very carefully studied over some 20 years, and this is likely, very likely to be correct. It has the name Barnard's star B. It's 0.4 astronomical units from the star, the same distance that Mercury is from the sun. It has a 233-day orbital period. It appears to be at least 3.2 times the mass of the Earth. So they're often called super-Earths. They're terrestrial planets, not gas giants. But because the star is so cool, this is probably at the surface temperature around minus 170 degrees Celsius. So, as indicated, the measurements were carried out over 20 years by 7 sets of precision instruments at multiple observatories around the world. And I've been, I think, to 6 of those observatories. So this is a comparison between our inner solar system and Barnard's star and its first discovered planet, Barnard's star B. So again, that planet is about 0.4 astronomical units from the star. And for the sun, we have Mercury at the same distance from the sun and the Earth at 1 astronomical unit. So this is an artist's concept of what that planet might look like if you were in this vicinity. Looking back at Barnard's star here. An artist's concept of maybe what the surface of the planet looks like. It's seen in the reddish light from the star. So during his lifetime, Barnard received a number of prizes and awards and honors for his discoveries, for the work that he did. And I have just a few of them listed here. Of course, Barnard's star was named after him. There's a crater on the moon, a crater on Mars named after him. A region on Ganymede, one of the moons of Jupiter, named after him. There's an asteroid, MGC 6822. There's a galaxy named after him. This is a galaxy about 1.6 million light years away in our local group of galaxies. There's a mountain named after him in California, and so forth. Okay, so that's the end of my presentation. Thank you.
Are there any questions?
How did he get from poverty to his appointment at the College of Planetarium?
How did he do it? By being a skillful observer. When he was quite young, he started with his telescope, making observations he discovered some comets initially. And because of that work, he was given a scholarship to Vanderbilt University, where he took courses. So he had some formal training, but essentially no elementary school at all. Almost no high school, I believe. Yes, Jim.
In retrospect, once they discovered with modern techniques, the planet around Barnard's star, did it compare to the earlier measurements?
No, not at all. The
Not at
earlier
all.
measurements were much more massive and were much further out.
What the data was, but does, has opinion said that there was indeed, he did indeed discover?
Van de Kamp did not discover anything because the data was spurious. And it was an artifact from having taken the primary lens off, cleaned it, put it back, made some adjustments. They did that several times. And that apparently resulted in this data which gave the appearance of maybe a planet in orbit. But that was not the case. Anything else? Yes, back there.
So earlier you showed the rotational period of Barnard's star.
Yes,
Probably a whole other talk, but how do they determine the rotational period?
How do they determine the rotational period of Barnard? That's a very good question. I don't know, I have the answer to that.
Jerry?
Yeah.
How long is Barnard's star going to live as a red dwarf?
As a red dwarf, it'll live pretty much forever. The less mass a star has, the cooler a star is, the longer its lifetime. And so this star, our sun is about a 10 billion year lifetime. For this star, it's probably hundreds of thousands of times longer than that.
So maybe into the trillions of years, potentially?
Almost certainly, yes.
Pretty cool. Thanks so much.